Okay, so for the next few minutes we're going to talk about two-dimensional video analysis. So two-dimensional video analysis is going to use a technique which has different names. It can be called videography or cinematography, and basically what it will allow us to do is use videos which are captured from a range of different devices. It could be a camera, it could be your smartphone, it could even be the webcam on your laptop, in order to preserve movement and elongate time so we're able to better identify what is happening. Importantly, and most relevantly for biomechanics, it allows us to measure things, and we know that's important for quantitative analysis. The key aspects of kinematics that you should recall from your previous instruction that can be measured with kinematic analysis is position, velocity, and acceleration. So what I'm going to talk about firstly is how we would set up a video camera to correctly and reliably collect kinematic data. The first very important thing is that you have a background that is contrasting to the participant or the thing that you are trying to record. For example, if you have a participant who is walking on a treadmill and they are walking in front of a white wall, it would not be a very good idea for them to wear white clothing because they wouldn't stand out from the background. So the first very important thing that we can use is a contrasting background. The second and probably most important thing, if we intend on measuring anything from our video, is a distance scale or something that we can use to calibrate our video image. Usually we utilize a meter stick or a meter ruler that allows us to convert the pixels in our real world, the pixels on our video image, to real world units. We can provide vertical or horizontal reference frames, and the scale must be in the same plane and the same distance from the camera as where the participant will be placed. I'll show you an image to give you a description of what that might look like in a second. So the first very important step when we set up for our video analysis before we record any of our videos is that we calibrate. A very important step that can never be forgotten if we want to measure anything from our videos. Once we've calibrated, we cannot move the camera. So this is what it might look like if we had a calibration volume or a calibration metric on a treadmill. We can also see in this case it acts as the contrast background. We can see that in this example there is a black board which has measured quadrants which we can use to calibrate our image. We can see that this has measures in the vertical going up and down and in the horizontal going back and forth. We can see that this is in the same plane of motion as the athlete, i.e. this board is directly parallel to the treadmill. We could not use this board, for instance, to calibrate. It has to be in the same plane. The board just behind this runner is in the same plane as he is moving in the sagittal plane. However, the board in front of the runner is perpendicular to his plane of motion. And in this instance, it would be suitable if we wanted to record in the frontal plane. The other important factor, which is actually slightly incorrect in this image, is that the reference frame is not the exact same distance away from the camera as the participant. We can see that the reference frame in this example is just behind the treadmill. So in reality, it's probably about 30 centimeters further away from the camera than the person. When we do this in practice next week in class, you'll see how we actually overcome this when we do some of our own data collection. So we want the calibration frame to be parallel to the plane of motion, but we want the camera to be perpendicular to the plane of motion. This is important when we're measuring in 2 dimensions, and it also is important that we place the camera at the proper height. So if we go back here, if we were interested in measuring this participant's movements from his hip down to his toes, then we would want our camera roughly around the same height as his hip. We also want to make sure that the camera is facing directly towards the participant, giving us a picture like what we see on this slide now. We want to make sure that camera is stationary, so on a nice stable tripod. You'll get practice using the tripods in class next week and figure out how to set them up properly so they won't fall over and the cameras are nice and secure on them. Like in this image, we want it to be nice and bright. We want to be able to see the participant. We want to be able to see his or her movements without any difficulty. Now, when it comes to the camera, we have to change certain settings on the camera to match the movements we are trying to measure. You should remember this from the lecture we just covered yesterday, or maybe not yesterday, your last lecture. Sampling rate or recording frequency is very important, and we need to set that on our camera. We've learned about why it's important in our last lecture. It's going to be relative to the speed of the movement, and for the cameras that we have in the lab, it can be anywhere between 30 and 600 frames per second. We would classify high-speed cameras as over 100 frames per second. So this is another view of what it might look like if we were trying to record the movement of a person on the treadmill. This little blue camera-shaped object is my representation of a camera, and those little lines coming out are my artistic expression of what a stable tripod might look like. We can see that the camera is perpendicular to the plane of motion of the athlete. It's stable, it's a nice distance away, and although we can't see it from this view, it's at the appropriate height. The other important thing we see in this image are the lights. The lights are shining on the object, or the participant I should say, to make sure it's nice and clear, to make sure that we can see the participant and all of the movement. So the camera is perpendicular to the movement, and we can see good lighting in this example. So again, in class, your last lecture, we actually viewed this image. And what we can see here is a two-dimensional tracking of a baseball. So this is essentially a two-dimensional analysis. We are gaining information on the movement of this ball in 2 dimensions. We can see how far it moves from left to right horizontally, how far it moves from top to bottom vertically. We can see these white marks that I've placed on the wall, make sure that everything is lined up correctly. The green wall is a perfect contrast background. Everything is nice and bright. I can see the ball and I can see it clearly enough for it to be tracked by the software. Our next section will talk about 3D video analysis, but for now we're just going to finish this one up and talk about how we would analyze the data we collect in 2 dimensions. So we got a brief taste of it in our last lecture. When we looked at that baseball, we looked at its various data in terms of its position, its velocity, and its acceleration. But more often than not, we have more than one marker, and those markers are placed on the body. So it allows us to measure human motion, which is obviously most important in biomechanics. This image is from a data collection that Dr. Jensen was involved in some years ago, and we can see it's very nicely illustrates the markers we place on a participant. In this case, the markers are with reflective tape. With a shining light, they are quite illuminated and very bright, and very easy for the software or for the digitizer to identify. I have superimposed over this a nice little stick diagram, which is essentially what we are trying to represent when we do our data analysis and our digitization. So to try and illustrate what that looks like in terms of data we get, I've now placed a quadrant or a graph essentially on top of our stickman. because each of these illuminous markers has a position, and that position is going to be defined by our calibration. The calibration converts every dot in this image to an actual measurement in meters. So we can see now, based on what we can see on this graph, that the participant's toe is approximately 1.3 meters away from the origin. We can see that the spoke of the first wheel is located approximately 0.75 meters away from the origin. So if we figure out that, then maybe they're about 1 meter apart. So this is just an estimate. I'm just trying to use this example to illustrate what we can actually do in kinematic analysis. If we look at one specific point, like the way we digitized our marker on the ball, or the ball for our example in class last session, each of these illuminous markers is going to be digitized when we are looking at human motion. So this marker, for instance, present at the knee, is located on the horizontal 1.3 meters and on the vertical 0.75 meters. So we can track that marker just like we tracked the ball. We can identify its location or position, its velocity and its acceleration. But I know you all remember from our work last semester in ES417, or maybe some other biomechanics courses you've taken, where we might want to calculate an angle. And if we have coordinates for these other 2 points, of course we can calculate the angle of that triangle. I hope you all remember that from our previous courses. If not, we will get a chance to revise it when we do some practical work next week. Okay, so this slide, if it will load, it's just taking a little bit of time, but I'm sure it will momentarily load. I have some YouTube videos loaded in here just to give you a visual of what some of these measurements would look like in real time as we were measuring them. So both of these videos are actually from Kinovia. So this is stuff we can actually complete, or you can complete in your own time if you have interest in these types of things. We know that kinematics involves position, velocity, acceleration, and that position is very important to allow us to measure angles. So this video has a really nice illustration of how these angles can be measured when someone is cycling on a bicycle. So like the previous example, the knee, the hip, the shoulder, all of these angles can be measured just by using the position of the 3 points around that specific angle. Oh, go back. Now, we can also measure other things. Like I noted earlier, kinematics, and like I'm sure you all know, is made up of position, velocity, and acceleration. You're probably tired of hearing me say those words by now. But this rowing analysis is a really nice example. On the right here, we can see the position and velocity of those joints. So we can see position in red of the elbow, velocity of the wrist here in green, and we can see how they're changing over time. Again, we can see the position of the knee noted here. What we can see on the left, at the end of each stroke, they identify segments and those segment angles. Okay? So by identifying the location of various important body landmarks, we can see them identified on the rower here in black tape. We can measure kinematic variables from their performance. We can see the contrast background is in play here with the markers used, black tape on light colored skin, and also the background, somewhat dark clothes against a white background. One final thing to touch on in terms of getting that data. In class next week we will use a software called Kinovia. You've seen it just demonstrated in those previous 2 videos. I would encourage you to download that before you come to class to save yourself some time. The link is available on the Educat. But when we use Kinovia to gather our information, we do what's called digitization, where each of those markers needs to be clicked. It can be done manually, or if we're lucky, the software can do it for us. It's usually best if one person does that for every participant in a research study, as it increases the reliability of the data. That's the end of 2D kinematics. You can now go on to your next section.